Thank you very much for inviting me. That's very cool. I'm very happy to talk about this work that I basically started doing just at the start of the pandemic. So this is, official COVID work. Oh yeah, I have the laser. That's perfect. Okay, so it's a short seminar, so I'll have to jump right in because there's a lot of stuff I want to talk about. Okay, so just some general background. Hopefully this should be, most of this stuff should not be necessarily super new to you guys, but it's still nice to kind of give an overview. Let's say you're trying to solve a mixed integer neural program. So, you have some variables, integer variables x, maybe some continuous variables z, under some equality constraints and some positivity requirements. This is just a standard form for it. When you're trying to solve these kinds of problems, it's often useful to obtain dual bounds. For example, for branch unbound or for obtaining optimality gaps. And the simplest way to do this is through the LP relaxation. Just drop the integrability constraints. This is a linear program, can be solved in polynomial time very efficiently, and you get a dual bound. But you can do better than that, right? So in general, you might have some inequalities that are satisfied by all milk feasible points, by all points that are, partially integer that satisfy all your milk constraints. We call those valid inequalities. And what's nice about them is if you add them to the milk, you end up with basically still the same milk, but its LP relaxation might be tighter. And in particular, the dual bound you get might be better. And then valid inequalities are not guaranteed to necessarily, just a general definition. They're not guaranteed to necessarily improve anything. But if it cuts off some part of the LP, then generally we call them cutting points. So just some vocabulary here. What's kind of nice is that there's algorithms that have been found in the 20th century that, given a milk, can produce cutting planes in polynomial by construction. Okay. Cool. So I'm gonna talk today about really focus on one particular algorithm called Gomery's mixed integer cutting plane algorithm. At least that's how I call it. And that's kind of the prototype for these kind of things. So it works like this, basically. First, you take your milk and you solve the LP relaxation. And solving that, say with the simplex algorithm, you end up with a basis matrix, which is invertible. If you do that, then the GMI cuts are these inequalities. You have one per constraint in your problem. With some caveats. That is given of this form, where tree is what I call the weighted triangular wave function, which is this guy. These little curly braces are the fractional part of a real number. And then this abs thing is what I call the weighted absolute function, which is this guy. Okay, it doesn't really matter too much what these are. You can just take them as being, a definition. But I can tell you that they are valid inequalities. They're better than that. They're guaranteed pretty much to cut off the LP solution. If you add them to this problem, well, you end up with a new milk, which is equivalent to the first one, with kind of extended constraint matrices, but whose LP polyhedron is now tight. And in particular, since you have now this extended milk, you might start everything over again. So you could solve the LP relaxation again. You get a new basis matrix, call it maybe B1, and you can start just over again, recalculate new GMI cuts with this extended milk, and you can add them again, and you get a new milk that's even bigger, etc. So you can do this iteratively, and you stop when you are tired, basically, when you don't want to do this anymore. Okay, and now I'm just going to mention something very quickly that's kind of maybe here the only part that's kind of a bit weird about it. Probably haven't seen, but when we have this extended problem, say this, I wrote it as extended matrices A1, B1, B1, B1. Of course, these are really, define in terms of these guys. So when we have this second rank GMI cuts, we can of course re-express them if we want in terms of the original matrices, the original problem data if you want. And you can do that, it's boring, but you can do the algebra and you end up with something that looks messy like this, okay? And of course, you can do this with the higher rank cuts if you want. It just, the algebra gets really nasty really quickly, but in principle, you can do it, okay? I'll call this the second order GMI cuts. I'll call these guys the first order GMI cuts, and analogously, you can have expressions for all the higher order. Okay, so this is just some background. There's nothing necessarily new or novel in all of this. Now, what I'm gonna talk about today is this thing, what I call continuous cuts optimization. And the idea is as follows. So I just mentioned that the GMI rank 1 cuts are these guys, right? Okay. But what's interesting is that actually you could take this same form and replace like this guy. I actually point with the laser, it's gonna be better. This guy and this guy here, we could replace it with an arbitrary vector v, any vector v. There's no constraints on it. And this b minus 1, I could replace it here by an arbitrary matrix w. And then on this side here, instead of the 1, I need to have this guy instead. But this is actually, these are valid inequalities, no matter the v and the w. Okay. You can show this. And then you get the classical GMI cuts back by really choosing a specific value for w. Okay. So it's already kind of like the first point that I'm talking about. So you can really see these GMI cuts as really being part of a larger family of valid inequalities. They're not necessarily cuts. There's a lot of choices of v and w that are useless, but nonetheless, they're all valid. You don't lose anything by adding them into the problem. Okay. And in the same way, if I took my really ugly second rank expression, expression for my second rank GMI cuts, in the same way, I can do the same thing. It's ugly, but I can basically, really see my rank 2 GMI cuts as being just a specific choice among a larger family of valid inequalities, okay, with a very specific choice. Okay. And then in general, I have this for every rank, basically. And you have these families of valid inequalities that are parameterized by continuous parameters, v1, w1, v2, w2, v3, w3. Okay, now here's a fun question. Okay, so say instead of choosing the parameters, according to what the GMI separation algorithm tells us to pick, which is b minus 1b, b minus 1, b1 minus 1, b1, b1 minus 1, etc. What about maybe trying to find better parameters? Like what about other v's and other w's, right? So already it brings us the immediate question, maybe there isn't any better parameters. Maybe what the GMI separation algorithm, the classical algorithm tells us is basically optimal, to which I will answer immediately no. There are better parameters than those that are suggested by the GMI separation algorithm. So it's not completely pointless. The second question is, what do I mean by better? So I'll just make a quick definition here by what I mean is better. I'll mean it's better if the dual bound you get after adding them into the LV is higher. That's my objective here, is to get as high a dual bound as possible. Now, you can really see just this as a continuous optimization problem. Really, that's what it is. I mean, it's unconstrained. There's literally no constraints on the parameters. You have a bunch of continuous parameters, and your goal is to optimize some objective, which is, the dual bound that you get after adding those cuts in. The problem is that it's a really, really nasty nonlinear continuous optimization problem. It's not even, the objective is not even continuous, it's really nasty. For a while, we looked at this and we're trying to find a way, hey, can we treat this as just literally a continuous optimization problem? And we came up with some interesting algorithm, which is not very pretty, You know, it's pretty ad hoc, and it's maybe subject to improvement. But at this point, this is like an algorithm that we came up with that sort of works, and it works like this. So say you really wanted to try to find the parameters that maximize this thing, that just gives you the highest drill down as possible. You could do the following thing. You can first solve the LP relaxation for given parameters. You know, might randomly initialize them if you want, or maybe you can start off at the values that the GMI separation algorithm gives you. And then you're gonna take gradient steps to make the cuts try to cut off the LP solution of this guy. So you're just gonna start moving the inequalities to make the LP solution point, which is feasible by construction, unfeasible, so that you're gonna try to cut it off from the polytope. And then once you've done this, you can just resolve the new LP with the slightly different cuts. You're gonna get the new LP solution, and then you're gonna try to take gradient steps again to try to cut off this point. And you're just gonna alternate these things until you're tired. And the gradient steps, you need a step size. I picked it to be fixed. You could pick it probably to vary, you know, anything is really possible. So this is not super pretty, but it sort of works.
Didier?
Yes.
What is I in the equation?
Oh, so the thing is, you might have a bunch of cuts. So I'm just saying there here, like kind of like maybe try to take gradient steps so that on average, you know, those cuts are try to cut off the LP solution. Or if you want, alternatively, you're gonna just sum up the gradients for every cut. You know, it's just that I don't only have a single cut, so I have a gap for every cut. Yes, that's it. Oh, it doesn't play. That's so sad. I had made a GIF. That's very sad. Too bad, really. Maybe if I click on it, it doesn't want to. It doesn't want to play. That's so sad. I have a nice, I have a nice GIF here where you see the cuts start moving and blah blah blah. That's pretty cool. Well, too bad. But this was 32 geometric inequalities that were randomly initialized. So they started off kind of being away, and then they progressively moved and moved towards the polytope. That's pretty cool. Too bad it doesn't play. Oh, I know why. Yeah, of course I'm an idiot. It's a PDF. Yeah, that doesn't make sense. Whatever. Then we did a bunch of experiments on actually the same kind of problems that were used in a previous paper about exact combinatorial optimization with GNNs. And they are also available in the Ecole software that we've been developing at the chair. So these are set cover problems. They're binary problems. They're kind of big. There's like 1,000 variables, 500 constraints. And so what you see, this is in optimality gap. So in red, you have what the LP relaxation gives you. When you get to 0, you know you've solved the problem. And in light dashed blue here, you have what 32 Gomery cuts gives you, according to like the classical algorithm. And in a darker blue, dash blue, you get the 32 cuts, rank 2, sorry. So you first add 32 rank 1 and then 32 rank 2. Unsurprisingly, it's better. But what's interesting is what happens if you say start from these initial values and you try to improve on them. You try to improve on what the classical GMI algorithm gives using this algorithm that I described before. And it's quite cool. So, you know, for the first few gradient steps, nothing happens. Or maybe, you know, it's gonna happen a little bit, but it's not necessarily impressive, but it starts picking up and the optimality gap, the dual bound starts increasing with respect to what the dual bound you would get from the GMI algorithm. And you see that you have quite a lot of progress, and that's quite cool. Same with the rank 2. Presumably this would work. I only tried with like 2 rounds, but presumably presumably this would work in general. And alternatively, you might want to start from scratch. Instead of starting from the values that the GMI algorithm tells you, you could start from just random parameter values. We tried a bunch of initializers, and actually what seems to work the best is a orthogonal initializer. So you pick the W matrices to be randomly orthogonal vectors. Which is a very good idea that Maxime had, actually. So we could call it the Maxime method. And it works pretty well. At first, the cuts are far away from the polytope, so you actually get the same bound as the LP relaxation. But eventually, they move towards it, and they start cutting off the LP polytope, and you start having a non-trivial dual bound. And yeah, like seems to improve a lot. It looks like it eventually converges at suboptimal values, though, so that's a bit of a pity, but it's still pretty cool. Yes.
You can take off your mask.
Oh, that's fine. Doesn't matter.
Well, no, because people from Zoom are there.
Oh, they have trouble hearing me. Oh,
no,
okay.
no, currently, it works.
I'll take it out just in case.
Well.
Okay, sounds good. Same thing with other classes of problems. This is combinatorial auctions problem. So they're basically, this class of problems where you're bidding on items. They're pretty similar to set cover problems, and we have the same phenomenon. It works well as well.
The random start field is actually slightly better than the standard.
Yeah, it's actually interesting. Yeah, tough to predict really what's gonna happen. Yeah. So here, it was preferable to maybe a warm start with the GMI values. And this one, it's maybe better to start from scratch. Maybe you're less biased in local optimal or something. These are maximum independent set problems. They're not enormous, but they work. And these are capacitated facility location problems. They're pretty smallish, and by default they're mixed integer, but these are just the pure integer versions. But you do get some gains, although this one was a bit trickier. As you can see, especially if you don't warm start, you get stuck in a local optimum for a while and then it picks up again. So a little trickier, but still, it still is pretty nice in terms of results. Okay, so that's all pretty cool. But now we get to the real thing that's especially the coolest thing about this. And I was really hoping that I would have time to talk about it. So this is perhaps the coolest thing about it in the end, even though it's purely theoretical, but it's just a very interesting connection between doing this. And namely, I'm going to talk about subadditive neural networks, which is a thing that, this is the first time you guys hear about this. So get ready because this is very cool. So as you know, every linear program has a dual linear program, right? So for example, if you write it in this form, which I like a lot, it's my favorite LP form, equality with like positivity constraints, then the dual LP is of this form. It's a maximization with respect to some parameter W with some inequality constraints. Okay. And as you know, it's equivalent in the sense that they both have the same optimal value. And if you have the solution to one, it tells you a lot about the solution to the other. Sorry. Okay. So the question you might ask is, oh, this is all nice and fun. I wonder if there's the same thing about integer linear programs. Have you ever wondered about that? Is there duality theory for integer linear programs? Maybe for every integer linear program, there's another integer linear program that's kind of its dual in some way that has the same optimal value, and the solution to one tells you something about the solution to the other. So as far as I know, the answer is no. I don't think there's such a thing. I don't think anybody has ever found such a thing. But you have the next best thing. You have this guy. You have the subadditive dual. That's kind of a cool thing that was found in the late 70s, early 80s. So if you take any integer linear program, then you have an associated equivalent optimization problem that is equivalent in the sense that it has the same optimal value, and it mimics a lot of things about linear programming duality. in that if your original problem is a minimization problem, then its subadditive dual is a maximization problem. And the number of variables that you have in your original problem becomes the number of constraints in the new problem. And the number of constraints in the old problem becomes kind of the number of variables in the new problem. But it's not an integer linear program. Instead, it's an optimization problem over functions. In a very large class of functions at that, it's optimization problem over all subadditive functions. And I'm going to say what it is in a minute. But it's a functional optimization problem over functions that take as number of arguments the number of constraints in the original problem, so m, and yet subjected to n constraints where n was the number of variables in the original problem. So it's a very large optimization problem. You can call it infinite dimensional if you like, because it's over all functions in a very large class of functions. And just to be clear, a subadditive function is a function such that fx plus y is smaller or equal to fx plus xy. So subadditive functions include things like the absolute value, norms. It's basically the triangle inequality. But also other things. There's other functions that are surprisingly subadditive, like the fractional part, for example, is a subadditive function, even though it's not that norm. Subadditive functions don't have to be differentiable. They don't even have to be continuous. They're kind of. And an interesting concept to associate with them that's kind of relevant is they don't have derivatives, but you could define this function called its upper directional derivative at 0. So I'm going to shorthand as u ddz. But that's basically kind of its derivative at 0, except it's not necessarily differentiable. So you have to be a bit, very careful about how you define it, but it's basically its derivative. This can define this as a function, and this function I'm going to call f bar is going to be pretty relevant in one of my books. Okay, so this is all very cool, and probably you hadn't heard about this because it was found in the 70s, but has not really had much impact. So why am I talking about it in the first place? What's the point in talking about this in a talk about cuts? Well, because of the very interesting following connection. So the connection is as follows. Say I look at my continuous cuts optimization problem, right? By definition, if I expand what the LP is, this is, what the problem is, where C, A, and B depend on the parameters. Well, actually, C doesn't really depend on the parameters, but whatever. Okay. By LP duality, I can rewrite this in this form instead, right? So it was before max min, now it's max max. Okay, so far. Okay, now say I introduce the following functions. I'm going to have some fk's that are going to be the concatenation of its arguments and the triangular wave function at the parameters vk and matrices wk, where those are vectors and parameters associated with the function. And then I look at the function that's just the concatenation, sorry, not the concatenation, the composition of all those functions with finally some just linear function at the end, okay? So if I look at this guy, then what I can see is I can expand these guys here, do a bunch of algebra, and I end up with this guy. Okay, there's no deep theorems, there's nothing, it's just a lot of annoying algebra, so to speak, and just rewriting in terms of these functions, okay? What I have is I have the maximization of this FB, because basically this B theta is the same thing as this W transpose B is the same thing as FB. And then these constraints here are like the first lines are FA smaller or equal to C. And then I have a bunch of additional constraints that I can recognize as being the same thing as W transpose F bar K composed with F2. Sorry, this is K minus 1. Sorry, this. Oh, sorry, no, it's actually a composition, triple lines composition. So I have a mistake here. Anyways, and these guys here. Okay. So this looks a lot like the subadditive dual, right? Namely, the subadditive dual would be this thing plus the constraint that F is subadditive. The problem is, in general, my F here, all these FKs are subadditive, but
this composition here is not necessarily subadditive, because there's this great tragedy about subadditive functions that in general, composing to subadditive functions is not subadditive anymore necessarily. But we have this very nice little theorem that we proved that actually, if you look at these constraints, they basically guarantee subadditivity of the composition of Fs. Namely, you can prove that having these kind of conditions are exactly what you need to enforce subadditivity of the composition of the Fs. And so what you really have here is the following, that maximizing this guy is really equivalent to maximizing FB such that F is smaller or equal to C, and that F is subadditive by the criteria of theorem 1. How funny, that's exactly the subadditive dual, right? Except that it's a subadditive dual over a very specific class of subadditive functions, whose subadditivity is enforced by a specific criterion. And the form of these subadditive functions is a composition of smaller similar functions, exactly like a neural net. So basically, doing GMI cuts optimization is equivalent to solving the subadditive dual with a subadditive neural net with a very specific architecture. And that's pretty weird and pretty cool. And then in particular, if you look back, you see this and you look back at what the classical algorithm might do, then you really kind of start reinterpreting this as saying that the classical GMI separation algorithm is really trying to do some greedy layer by layer training of this subadditive neural net. Whereas when you do continuous cuts optimization, it's maybe something more like end-to-end training of the subadditive neural net. Yeah, this is pretty crazy. That's it. You guys have any questions? Yeah.
I was wondering on the 2 slides, the equivalent of the dual problems that you had. How is the form of the function? Because it can have like a vector as its parameter and also a matrix.
Sorry, so which
it's
for that?
Yeah, it's this one or something later. But I don't know.
Further from
like
in the subadditive part?
Yeah, yeah. Yeah, exactly. This one.
Sorry. Oh, this thing here. Yes, that's just bad notation that I didn't explain. Actually, it's pretty good notation. So it's just so you're right. It takes a vector as the same dimension as B. So this is just my funky notation for I apply the function to every column of this matrix.
Okay. Yeah.
Yes. So this is just really compact notation for n inequalities where n is the number of columns here and n is also the dimension of C. Okay. Yeah. So really this is just, if I call AI the ith column of A, this is just FAI smaller or equal to CI for every I. So sorry, I should have explained. I like this notation a lot. It's really nice because it makes the analogy here really strong. So yeah. Yeah. Yeah.
Sorry, and also in a few slides after that.
Yeah.
Yeah, this one.
Yeah, this is like where I throw under the carpet the algebra, but
yeah.
I would have given more details if I had more time for this stuff.
I was wondering about the is there a relation in the objective you have f of b according to theta and w. So is it like, does it become a constant or?
Sorry, what is the constant of theta?
You have the dual problem that is max of theta and w and of f of b. Is it still related to the variables, the f of b? Because you don't have the...
really w transpose b theta, I mean, you have to expand it, but it's the same thing as f b.
Okay.
F here, also f, again, I'm kind of like hiding notation because otherwise it would be too much, but it depends implicitly on theta and w. Right?
Okay.
I actually on this slide I used to have the theta and w. Then I figured I'm gonna remove it because it's gonna be too ugly. But maybe I should have kept it. Yeah.
No, it's cleaner this way.
Yeah. So it implicitly depends on theta and W. Yeah. Because that's what it is here. And then theta is just like the V's and the W's. Something like that. Exactly. Yes, maybe.
How do you take the derivative with regard to phi?
Yes, for the gradients.
Yeah.
Yes, so automatic differentiation software. So we do it in PyTorch, actually. But yeah, oh, do you mean for the LP?
Yes, yes.
Oh, well, actually, you don't need to take the gradients with respect to the LP because I avoid this because I solve the LP relaxation, but then here I fix the LP solution. So I don't take the gradient with respect to the solution. I only take the gradient with respect to the cuts, and the cuts are these really ugly functions, basically. Here, well, I mean, there's this guy, and then there's this guy, and then this guy. So they're really ugly expressions, but you can express them recursively, and with an automatic differentiation package, you can do it. Like you can compute these things basically. So I use PyTorch, but because I just used to do machine learning, but yeah. Presumably, you could, I mean, maybe there's like more efficient ways of computing the gradients.
My question was more about undetected the gradient of the fractional part.
Oh, that's a good question. Yes.
Did you just assume that the gradient is the identity?
I just assume it's never integer. I just assume that the gradient is let me think about it 1 second again. Yes, I basically just assume that the gradient of the triangular function of this triangular function is 1 everywhere. Yeah, yeah. So which is something that machine learning people like to do a lot. They take non-differentiable functions, the functions that are not differentiable at specific points, and then they're like, numerically this never happens. So yeah, gradient is well-defined everywhere. So I just do the same thing, yeah. I actually tried doing something kind of more clever because the function, I didn't show the graph, but it looks like, it's like a triangle wave. So I kind of thought about doing like an approximation with like a sinusoid, kind of like, oh, it's gonna have better gradients, but it didn't really change very much in terms of like, ability to like improve the results. So yes, that's how I differentiate it, by assuming it's differentiable everywhere when it's really isn't. Yeah. If you have better ideas, I'm open. Yeah.
Was there another question?
Yes, I think so. I think Sam had a question.
Oh yeah. So I was also going to ask a question related to the gradient. Looks like you are calculating like the maximum violation of the healthy complex, but the criteria you mentioned is like you want the most improvement in the objective. Kind of different than.
So yeah, I really want to improve the dual bound, but how I do it is by trying to make the cuts violate as possible. Yes, yes. So it's kind of a proxy, which is not ideal, but yeah. Exactly.
Can I ask you a question?
Yeah, sure.
So it's more of a practical question on the first part. So when you do, like you want to train, basically this is like continuous optimization.
Yes.
So what you do is that, I'm just trying to rephrase, basically you detach from the LP solution. So in a classic algorithm, you will get an LP solution at a cut, and then like iterate following the path that the LP solution is giving you. Whereas here, you basically generate this B and W in a way that you don't care if there are phases of the LP solution or whatever, and you just add them.
Yes.
In your experiments, once you add the cats, right, you basically never remove them, right?
Yes, you can answer. Oh yeah, but yes, so that's something that's kind of like weird about it. It's kind of like we agree on the number of rounds ahead of time. We kind of say, I'm gonna do 5 rounds, and I'm gonna decide how many cuts I'm gonna add a priori, 32 in each round or something like that. And it's just like from start iteration 0, I have 5 rounds of 5 rounds of cuts. You know, rounds is maybe not the right word anymore, but let's say maybe the better way to phrase it is I have 32 rank 1 cuts, which are cuts of this form, and 32 rank 2 cuts that are cuts of this form, which is part of the reason why I took some time to write out those slides so that it's like less confusing. But that really be mean by rank 2 cuts of this form, just different algebraically.
No, but I mean, this question I think is important.
Oh,
so the cuts are actually removed. So what you can think about this procedure as a cleaning up of the cutting planes over time. So you produce the cuts by optimizing over this W, and then you add them.
You see the bound.
You see the point, and then you can throw them away, and then you continue to add the next 32 cuts, which are still rank 1, and you keep going like this. But it's in the way I see it, is a way of distilling these 32 cuts. You're deciding from scratch that you want 32 rank 1 inequalities, and you want to try the best ones in order to prove the bound. Yes. But I mean, in a general cutting plane approach, you will add the cuts, you keep them in order not to lose memory of what you did. What we believe is that the neural network is keeping this memory and is able to actually optimize this even if you don't keep the cuts.
Yes.
But of course, it's not mono, right? I mean, it can go up and down.
Exactly. Yeah. So that's another one way of seeing it if you guys want, which is I have my 32 cuts. I slightly update them and I throw away them and replace it by the slightly different ones. Me, the way I think of it is more like I'm just changing the parameters, but if you rather think of it that way, that's fine. And in particular, when I solve these LPs always have the same size. They never grow.
Yeah, I think the interpretation is you want to keep like kind of a training memory of whatever you did before, but like my say more optimization perspective was you don't want to keep more cuts than you actually should have because otherwise
absolutely yeah. So
that answers to my question.
Exactly, yeah. But like Andreas says, the downside of that is you're not necessarily monotone anymore. At every iteration, you could decrease. In fact, it does decrease. In fact, those plots are really, I didn't mention it, but they're really kind of like the best so far. So when you see these things here, probably what happened is that it went down, then it went up a little bit, and then it went down again. Yeah, that's basically what happened. But since it's only the best man you ever found so far, it really matters. I figured that it was okay to like that. But, yeah. Do we have any questions online?
Maybe. Well, no, I think no. I didn't check the chat. No, so far no.
Thank you very much.
Cool.
Thank you.
Switch with next.
Just gonna check one thing.